Honors Chemistry, and welcome to Chapter 14. And just in case you didn't pay attention to anything else before this moment, ding, 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 last formal chapter of the school year. Not to be confused with last set of grades or last thing we'll cover, just last formal chapter from your book. Okay, so anyway, Chapter 14 talks about acids and bases. So you should be a little bit familiar with the concept of what is an acid, what is a base, and the concept of pH as an indicator of the relative strengths of acids and bases from 8th grade, and may have been reiterated again last year. This year we're just going to talk a little bit more in depth about it because it is just one of those really important life topics. So first of all, properties of acids and bases. So when we're talking about acids, we should know things like they tend to be sour, right? Common life example includes, right, vinegar. All vinegars, so any type of vinegar includes some acetic acid, right? The percentage of acetic acid tends to dictate a little bit of like how sour it is when you eat it. In addition, all the sour candies, right, have citric acid or something similar to that as a component, right? Like that white powdery stuff on all those weird sour candies. All right, they also react with metals, right? Now, your guys' book says that it dissolves metals, and then there's a little side note there. That side note, super duper important, because on an assessment, if you tell me that acids dissolve metals, I'm not going to give you any credit, right? Because that's not true, right? When we say dissolve, what that means is that implies something closer to a physical change than a chemical change, right? Whereas that's not what happens here. Acids react with metals, which, going back to chapter 7, right, what kind of reaction is that? Right, it's a single displacement reaction that produces a salt and hydrogen, right? So if we think about HCl, for example, aqueous, plus say magnesium, right? We get magnesium chloride, aqueous, and we get some H2 gas, right? So what that really means is magnesium is now part of this aqueous compound, right? So it appears to have dissolved because you can't see solid metal anymore, but that's not the most accurate way to say what's happening, right? It has reacted with the metal such that now we have aqueous ions instead of solid atoms like we did before. All right, so bases, right? Bases are known to be bitter, which is different than sour, right? Bitter, evolutionarily, is something that humans, and actually I think other critters too, tend to avoid, right? Because bases tend to be, a lot of them are poisonous, right? Consumed at a high enough level. Now, though, if you look at a lot of like those new greens that everybody is supposed to eat because they're so good for you and so healthy, a lot of those are actually quite bitter. But I guess it turns out that those bitter things that are not bad for you are actually quite good for you, and we are supposed to eat a lot of them, even though they're bitter and not terribly delicious. Anyway, moving along, bitter. Slippery is the other one, right? So if we were to rub something basic with our hands, right, for example, it would feel slippery because that base is reacting with the oils in our skins and we end up with a slippery feeling, right, which is part of why soaps, for example, right, classic soap tends to be pretty basic, which then leads to why it feels so slippery on our skin, and depending on the type of water that you have, right, if you go to a place that has really soft water and you're using a traditional soap, sometimes it feels like for the life of you, you cannot rinse it off, right? But bitter and slippery, a lot of cleaning products are basic, right? So going back to where we would find these, right? Sour, right? A lot of foods, right? For acids, right? Since they react so well with metals and certain metal compounds, right? Like carbonates, for example, right? Which tends to be one of the common things that lead to deposits, right? Around sinks and things like that, right? Things like CLR and whatever that are meant to remove deposits often contain acids. Bitter, right, tends to do with more with cleaning products. That's where we find a lot of our cleaning products are basic. Though we can actually, depending on where you go shopping for your groceries, you can find potassium hydroxide, sometimes known as lye, in the food section because it is something that is used to help prepare corn for certain cooking processes, right? So it's not foreign to everything, and it's not only used for cleaning, right? Okay, moving along. So this is just some basic properties of acids and bases, life things we should know. Oh, by the way, where do we carry around acidic stuff all the time? right, in your stomachs, right? That's where that first round of digestion occurs. I guess the first round occurs in your mouth. So that's where the second round occurs. Okay, moving along, Arrhenius, acids, and bases. So we have several different, there are lots. Your book covers 2 definitions of acids and bases, and these are the 2 you're responsible for knowing. Depending on the circumstances where the acid or base is used, that's what determines which definition is better, right? Arrhenius is one of the oldest and most traditional ones, where we say that acids are things that produce or increase the concentration of H plus in solution, right? And so we'll talk a little bit more about how we could know if that's happening, right? But HCl, going back to how we write the formula, is composed of an H ion and a chloride ion, which then together means we end up with H plus and Cl minus in my solution, right? This increases the concentration of H plus, therefore it is an acid, okay? Just a quick note, this doesn't really look like that in solution, right? So when we say H plus, really what that means is that H plus is going to react with water to produce this, which is known as a what? Right, this is a hydronium ion, right? As in H pluses don't just hang out by themselves, right? H pluses being also known as a proton, right? Don't just hang out by themselves, right? In the presence of water, they're actually going to go interact with that water molecule and produce this in solution, right? So this is like a shorthand. Okay, moving back to the bases, right? Obviously, this is an ionic compound. It's aqueous, which means it's soluble in the water, right? Which means that we end up with sodium ions and hydroxide ions, which means that it increases the concentration of hydroxide in solution, which gets this labeled as a base. So any of our soluble hydroxides would be classified as bases. Yes? Make sense? All right. Now, then that brings us to the Bronstedlowry definition, which is a little bit more thoughtful. So these are only going to be for aqueous phase reactions, right? Which is most of what we're talking about. And here we're talking about proton donor and proton acceptor. Going back to what we said over here, right? Proton simply just means an H plus, because an H starts with what? 1 proton and 1 electron. If we donate 1 proton to become H plus, 1 electron, right? All we're left with is a proton. All right, so HCl, so if we're talking about Bronstedlowry, we're going to say that it reacts with water, and then we're going to get our H3O plus and our Cl minus. So this is just the more thorough picture of what we saw on the other page, right? Where this proton now finds itself attached to that oxygen, and that's where we get this. And then we have that chloride ion, right? Now, your book also talks about Bronstedlowry pairs. So let's go ahead and give some labels here, right? So here, this is protonated, and if we remove a proton, we end up with that, right? So here is our acid, and this is its conjugate base, the deprotonated form, okay? If we look at the other set here, this is our other pair, where that means this is then my base, and this is its conjugate acid, right? Where base again is deprotonated and acid is the protonated form, okay? So if we're trying to commit things to memory, right? Acids are protonated, bases are deprotonated, and in every Bronstedlowry process, there will be an acid and a base that exchange a proton, okay? That's what's happening. Right. Okay, so coming down here to NaOH, bases are a little more thoughtful. So in here, what this means is we're going to start with 2 parts, right? So first we're going to dissociate this, right? And then we're going to take that OH ion and react that with some water. And then we're going to come up with, which seems redundant, and it is, but strong bases, so this would be a strong base. Writing a Bronstedlowry process for a strong base is a bit redundant. That's just how that is. So then what that means, so the concept of your Bronstedlowry pairs is a little bit weird here, but if we talk about a weak base, where most of our weak bases are going to be nitrogen-containing compounds, right? Ammonia being the classic one, right? Where that is going to then do this. Where if we look at that, right, now we can do our conjugate pairs, right? Where we have this and this are different by 1 proton, right? Where this has 1 more proton, right? This one has 1 less proton, which means this is my base. and this is its conjugate acid. Here, that means this is functioning as an acid, and this is its conjugate base. Yes, does that make sense? Right? So again, Bronstedt-Lowry pairs for a strong base don't really make sense, because a strong base is just going to dissociate and directly influence the concentration of hydroxide ion. But if we have a weak base, it's going to react with water, which means that my base is then going to take a proton from water, and water now is going to, having lost a proton, is actually just going to be my new hydroxide ion. Yes? All right. So that's our Bronstedt-Lowry pairs. So then going back to make sure we hit all of our important definitions, right? Water, since it's capable of acting as a base and accepting a proton, or acting as an acid and donating a proton, we could say that water is, right, amphoteric, right? Capable of either donating or accepting, which is super duper important because that's the foundation for calculating pH in the next section. All right, thank you for listening. Be good, and I will see you soon. Bye.